morning, everyone. We are the Wind Turbine Train Tunnel Application Group. Our team members include Keon Vereen, who is our experimental designer. I'm Deborah Watson. I was a CAD designer. This is Jonathan Mooney. He was our data analysis. And this is our team lead, Carlos Velez. He was our researcher. Our presentation this morning will include our introduction, explain our experimental apparatus, our results, benefits, and future work.
As many of you know, subway and train systems are one of the primary forms of transportation for both passengers and cargo. And even in Florida, new high-speed train systems being proposed that would connect Orlando with Tampa and Miami, allowing high-speed transit throughout all of Florida. This research-based senior design project hopes to introduce a new clean energy technology which can be installed in pre-existing and new train tunnel systems. You see, as a train travels through a tunnel, it pushes a lot of air. It acts similar to a piston. And eventually this air will build up in pressure and it'll slow down the train and also cause discomfort towards passengers. So what engineers have done to alleviate these pressures is they install air shafts in all train tunnel systems. This allows the air to flow from inside the tunnel outside at high speeds. Our project seeks to investigate experimentally the potential power of the airflow in these air shafts. By analyzing this flow, we can determine the performance of a theoretically installed wind turbine within this air shaft. We also want to determine which application would work best. Do subway, cargo, or high-speed trains generate the most energy? Additionally, if we harness this available energy and pre-existing energy, we are in essence recycling some of the energy that was created by the train.
All right, hello everybody, my name is Keon Vereen.
Right here, just turn it on.
In order to analyze the flow inside of the ventilation shafts, we created a scaled-down experiment to model after the three different train systems: high-speed, cargo, and subways. In the bottom picture, we have a launcher that can launch train models up to 165 miles per hour true speed into our tunnel section, where we have our mounted ventilation shafts on top, where we have sensors inside to measure the pressure. And then from the pressure, we can then calculate the velocity and the potential power output from that. And then as the train model is launched through the exit of the tunnel, it is then slowed down by a damper that gradually slows it down. Oh, and now we're going to start one of our videos, which is a true speed, high-speed train model being launched at 102 miles per hour. Pretty fast, yeah. So that's 102 miles per hour. So the next video is high speed at 163 miles per hour, where we slowed it down frame by frame so you can actually see it this time.
Hello, I'm Jonathan Mooney. I was the data analyst on the project. In order to figure out the best application for this research, we conducted two trade studies. One to figure out the power generation versus the velocity of the train, or whatever model we were testing at that certain time. The other was the difference between each application themselves. The graph on the left, as you can tell, showed that the subway was the best application. It had almost an exponential increase over the other applications after it reached its maximum speeds. Using these results, we were able to show that theoretically we could generate over half a kilowatt hour per train passing, which for any typical application for a subway, they pass these ventilation shafts anywhere between 300 and 350 times per day. That amounts to about 150 kilowatts an hour, which is enough power to actually power about 5 houses on its own per day. From this, we derived that if this kind of system were implemented in any typical subway system, run 365 days, with 300 to 350 crossings of the ventilation shaft, we could save or put enough power back into the grid that amounts to about just over $7,500. Obviously, this has shown that ideally we could do future research to figure out what would be the best way of harnessing this impulse energy that we were seeing. This is just a sample application of how we could theoretically collect the power. As the train approaches the turbine itself, it spins in one direction due to the compression wave. As it passes, it reverses direction and moves on with the suction effects. We would now like to thank our sponsors, UCF and Progress Energy, and our advisors, Dr. Go and Dr. Scott Martin. please visit our table in the back right-hand corner of the Progress Center.
Thank you.
Thank you.